What we would like to do now is to address the mentioned complexity in multi-axial combined loading, in other words, and be able to predict when we have a complicated state of stress. So the complicated state of stress arises from the presence of multiple stress components. So if we represent the state of stress at a point geometrically with our usual depiction, so now these are my coordinates x, y, and z. So what we are doing, if you like, remember, this is not a cube of material. I have, say, a structure, a cylindrical beam, let's say, and that cylindrical beam is subjected to a torque, it's subjected to a bending moment, perhaps there is even a tensile load, and I am interested in the state of stress at a point, say, where the state of loading gives rise to a very critical loading, say this point at the top of the beam where the support is. So at that point, the state of stress is represented with that picture. So in general, there will be normal stresses, as well as shear stresses. So let me not write all the shear stresses presently. I'll just very quickly indicate them over here with these blue lines. So I have both normal and shear stresses. So I'll just write tau here. There will be 3 taus, well 6, but it's symmetric. So overall 6 independent stress components. And that's what I would like to formulate eventually my failure criterion through, because I know that even in the simple case that we have just looked at, the presence of 3 normal stresses and their values, whether they are present or not and what their values are, determines the value of failure with respect to ductile yielding, for instance, and if it happens at all, right? And for that matter, I can imagine that the presence of shear is also going to influence whether or not failure will happen. So that is what I would like to address now. Now, what we have learned from our discussions associated with principal stresses is that I can convert this picture to the principal picture. So in other words, I can represent the state of stress at the same point with a cube that is oriented along the principal directions and along which there are normal stresses sigma 1, sigma 2, and sigma 3. So this is the principal direction 1, that's principal direction 2, and that is principal direction 3. So that representation is equivalent to this representation, and therefore I might as well consider the question of whether failure occurs or not in terms of the original picture, but in terms of the principal stress picture. And this has a conceptual advantage because here there are 6 independent components of the stress, whereas here there are only 3 independent components that influence now whether or not failure is going to occur. If there is only one stress in general, so it's essentially uniaxial loading, I know when, for instance, a ductile material will yield. It's going to yield at sigma naught. But if there are 3 principal stresses, then the question is, when does yielding occur and if it occurs at all? And the same question is going to be asked for a brittle material as well. So therefore, now what we would like to do, what we will do is we will write a general formulation of how we think about failure. So what we've said is that we have a principal picture that is essentially equivalent to the original picture. Now, here I will put an exclamation mark, which I will come back to in a second. So this picture I'm saying is equivalent to that picture, and therefore I might as well work in terms of the principal stresses. And therefore, this is the following thing I will do. So first of all, if I have a uniaxial loading scenario, I know that failure occurs at a certain critical stress. Failure for me at this stage might mean the yield strength of the material or the ultimate strength if I'm working with a brittle material. In either case, we will have a certain critical value of the stress that we do not wish to exceed. So C for critical. Now, if I had a pure uniaxial normal loading scenario, I know that I wouldn't want to exceed that value. In other words, the stress I'm applying should be less than or equal to the critical stress, which is a material property, which is equal to sigma naught if it is a ductile material, if there is considerable yielding, and it is ultimate strength if it is a brittle material. Now, if, however, I do not have a state of uniaxial loading, well, then the formulation is not going to be easy because each stress component is going to influence the whether or not failure occurs or not, and at which value. And moreover, I cannot use any one value because the right-hand side is a material property, but the left-hand side is a certain state of stress. So for instance, in the previous example, if I choose this to be sigma y, well, the right-hand side now does not become a material property. Sigma y is less than or equal to sigma naught in one case, sigma naught over 2 in some other case, and it doesn't fail at all in some other case as well, right? So I don't want to use any single component. What I want to do is I want to make use of all of the components, and what I will do in the presence of multiple stresses is, instead of using one stress, I'm going to combine them into a so-called equivalent or effective stress. So that's what sigma bar stands for. It's an equivalent or effective stress. And it is, notice, importantly, a normal stress because the comparison value is a value that comes from a uniaxial tension test. Which delivers a limit to the normal stress which I can apply on the material. Okay, so therefore the idea is, well, I have a state of multiaxial stress and I'm representing it in the principal picture, and I know from a normal uniaxial state of stress, a tension test, what the critical value that I can apply is. But if I have a multiaxial state of stress, what do I do? Well, what you do is you convert your state of stress to a equivalent or effective uniaxial normal loading state. So you calculate the equivalent or effective normal stress. How do you do that? Well, you construct a function that takes in all the values of the stresses that you apply presently in terms of the principal picture and spits out a single normal stress. And then you can think of this stress now as if it were coming from a uniaxial tension test, and therefore you compare it against the critical value that comes from such a test. Okay, so original state of stress, we convert it to the principal picture. Now there are 3 normal stresses only appearing in that picture. We put them into a function, a criterion. So this is going to be our criterion for failure, so F for failure if you like. And that criterion depends on the material. Aluminum will have a different criterion, or glass will have a different criterion, for instance. Primarily the criterion will depend, you'll see, on not specifically on whether it is aluminum, steel, or glass, but on rather whether it's ductile or brittle. So the criterion will take that state of complicated state of stress, convert it to an equivalent effective normal loading, and then compare it against the critical value that comes from a test where the loading is exactly in that form. So this, therefore, is going to be our, if you like, stencil. And we should remember this stencil. and we should remember the ideas that go into the stencil. In particular, we should remember that the critical value is a value that's associated with the uniaxial tension test, and therefore that if this state of stress is actually a uniaxial tension test, it should still be satisfied. Okay, so in other words, when sigma bar is simply sigma y, let's say in the very first example that we gave in the previous slide, largest value sigma y can be is, in the previous example, sigma naught. Simple, right? But if there are multiple stresses present, then what is this criterion is now our leading question. How shall I formulate it? All right, so now this stencil, let me call it a stencil or template, is going to be used again and again. We're gonna provide specifically 3 different failure criteria, 1 for brittle materials and 2 for ductile materials. There are many failure criteria. Just like in the rest of the course, we are giving you representative forms, representative ideas essentially, to expose you to the idea of such failure criteria. Now, before we proceed to remarks, remark number 1. Well, what we're doing is we are proposing to convert a complicated state of loading into a effective normal loading and then compare it against a value that has to do with the uniaxial tension test. Does that physically mean that materials fail because the normal stress ultimately exceeds a certain value that has to do with tension? The answer is no. The material may not be failing because the ultimate tensile strength, let's say, of the material is exceeded. The material may actually be sensitive to the amount of maximum, say, shear that is present throughout the structure. At a given point in the structure, the material fails, let's say, because the maximum shear stress is reached. So you may want to sometimes formulate this criterion in a slightly different way. What you may want to do is you may want to calculate an effective shear stress, and you may want to convert that or compare that against a critical value of the shear stress. And if you know the critical value and if you have a function, now let's call that another function g, that is able to give you what that value is, then you can predict whether failure occurs or not. Just like here, if we're less than sigma c, if sigma bar is less than sigma c, we're safe. If it is equal, we are on the limit of the elastic zone, so we're about to fail, assuming the safety factor is 1. In general, there will also be a safety factor. And eventually, if I have a design where the loading is such that this quantity appears to be larger than that, well, that's a bad design. You better go back and review it. So the same idea applies here. I calculate an effective shear stress. If it is less, then I'm safe, equal on the onset of failure, and if I'm outside, that's a bad design. And as I said, in both cases, you can have a safety factor. In this case, the safety factor is going to be, let's write it over here, safety factor on failure, xc, let's say, is going to be sigma c over sigma bar. Okay. Now, however, what we can keep in mind at this stage is the following. Well, remember, for instance, the Mohr circle. If the material is indeed sensitive to the maximum shear stress, the absolute maximum shear stress, how do I calculate it? Well, the way I calculate it is I look at the maximum shear stress in each plane. In the 1-2 plane is that minus that divided by 2, absolute value. In the 2-3 plane, sigma 2 minus sigma 3 over 2, absolute value. In the 1-3 plane, difference divided by 2. And I take the maximum among those values, and that would be the absolute maximum shear stress. So if the material is at a given point going to fail because the absolute maximum shear stress is going to exceed a certain value, in this case the critical value, then I can formulate my criterion in terms of the shear stress. But notice I am calculating the critical, the effective shear stress, and compare it against the critical value, again by making use of sigma 1, sigma 2, sigma 3. So one way or the other, you make use of the principal stresses. So either formulate it like this or like that, you will reach eventually the same decision, whether material fails or not. Now, but the two will eventually be the same expression, the same, let me say, formulation of whether failure occurs or not. The two formulations, however, will differ mathematically. This function will not be the same as that function. But if in this normal stress, effective normal stress formulation, if I predict failure, in the effective shear stress picture, also failure will be predicted in exactly the same limit to sigma 1, sigma 2, sigma 3. So let me put a big parenthesis to what I have just said. If you like, you may want to go back and remember this discussion, because I'm going to come back to it and I'm going to use sometimes this alternative stencil instead of that one. Nevertheless, all of our stencils do fit in that form, so I will prefer to formulate them in this form because they are, in my opinion, a little bit easier to remember, but you may find this to be easier to apply, which actually is the case for me, at least for one of the criteria. And what you can also remember, and you may want to come back to this remark as well, the safety factor for a given state of stress, irrespective of the form of the criteria that you are using, will always predict the same safety factor. So that will not change. All right, so back to our stencil. I had two remarks I said. The first one is that I'm formulating everything through an effective or equivalent normal stress. You can do so through an effective shear stress if that is physically more relevant. However, this is the one that we are going to prefer, and in both cases anyway, the determining factors are the principal stresses. Let me come to the second remark now. The second remark is very simple. Well, we are saying that the two pictures are equivalent, and we're taking, instead of the 6 independent components of the stress, these 3 independent components. Well, but there is a conceptual difficulty here. Now, we seem to be insensitive in the formulation of our failure criterion to the directions of these principal stress. In other words, I don't care if this is, let's say, 100 MPa, this is 50, this is 30, 100, 50, 30. And the material will fail because, let's say, the maximum normal stress you can apply is actually a certain value. So I only need to monitor the maximum normal stress. In this case, 100, 50, 30, 100 is the maximum one, and 100 is in that direction. Well, and then I try to decide whether failure will occur or not. Now, but I can imagine that in some cases, perhaps the orientation of that 100 is important. Perhaps if I apply to a material 100 MPa in that direction, it will fail, but in some other direction, if I apply 100, it will not fail. And what we are formulating here is a stencil, a template, a way to think about failure that does not take that into account. So what does that tell me about the type of material that I am trying to formulate? What does that tell me about the material behavior? So take a second to think about that. So if you have paused, let me rephrase the question once again. So what we are saying is that suppose I have a sheet of aluminum, okay? And I cut out a test specimen from it, and I pull on it in that direction. It fails at a certain value, sigma naught, okay? And I cut out a specimen in another direction from the same aluminum plate, and I do a test. It fails also at sigma naught. And I do a test with a specimen cut out in some other direction. Again, the specimen fails at sigma naught. Well, what does that tell me about the material behavior? And you can now try to make a link clearly with the same question that we asked in the context of elasticity. Will the Young's modulus that I measure in all directions be the same in all of these cases? The answer is yes. And why is that so? Because the material is isotropic. So the question of isotrope is central to our efforts in modeling material behavior, including failure as well. So just like in elasticity, now I have a concept of isotropy that applies to failure. If the material has the same failure limit with respect to all directions of loading in an uniaxial tension test, or for specimens that are taken in different directions from a plate, then that's an isotropic material. And now, what is the case of an anisotropic material? So this is the case with a carbon fiber composite plate. So in this case, there are fibers that run roughly in the horizontal and vertical directions of the plate. So I can imagine that those fibers are going to, the carbon fibers are going to significantly strengthen the specimen that I cut, let's say in that direction. And there are also fibers running in that direction. So if I cut a specimen in that direction, it will also be very strong. But there are no fibers running in the other direction, or at least I'm not going to load the specimen in the optimal direction if I pick a specimen or cut a specimen that lies in some skewed direction. So that specimen will probably give me a strength that is less than the other two directions. And that's because just like the elastic behavior of this material, composite material, is orthotropic, the failure of the material is probably also going to be orthotropic. So it is not isotropic, it is going to be anisotropic. So what we have essentially said in our discussion implicitly is that the directions of the principal stresses do not matter, and hence only the values matter, which amounts to saying that we are assuming isotropic failure in addition to isotropic elasticity. Okay. Certainly we could attempt to formulate failure criteria for anisotropic materials, but we are limiting our discussions to isotropic materials just to give you an idea of at least how failure works for multi-axial loading scenarios for materials.